Jai Hind everyone. I Neeraj Sharma, Assistant Professor EC Department at Ajay Kumar Garg Engineering College, Ghaziabad. I am before you to present the video lecture for the series, complex topic series. So here in this lecture, I have chosen the topic linear phase characteristics of an FIR filter for the subject digital signal processing as per the accredited curriculum. Its course code is BEC, subject code is BEC 503. So this because of DSP, in the DSP subject we have discussed regarding the filter realization and the designing part. So where basically we have studied the realization for the two type of category we will discuss here for the filters. The first one, that is the IIR, infinite impulse response, and the second one, that is the FIR filter. That is the FIR is, that means what? Finite impulse response filter. So while we will design, when we will design the FIR filter, with the help of some realization and some designing techniques, when we design it, so the first one, some characteristic has to be taken into the mind that that should be satisfied. Then we are able to move on to design the FIR filter. The basic characteristic, that is the linear phase characteristic. So that what is this linear phase characteristic? If we will satisfy this linear phase characteristics, then the FIR filter designing can be possible. So what is it and how it can be checked or how it can be derived, we will discuss in this lecture. So in this, for the realization of this, what is the basic characteristics for the FIR filter? So for that point of view, we have to go for the we will discuss first of all we will see the response, what the impulse response we are getting for any system which has to be designed. So in this series, so just now we will discuss the discrete time Fourier transform of an finite impulse response of h of n, which is given by the h of e raised to power of j omega, which is equals to summation of n is equals to 0 to m minus 1 h of n e raised to power minus of j omega n. So this will be the formula how we can evaluate the magnitude and phase response. So we have just Hn is simply a response of any FIR filter. So that which is its Fourier transform is given by this function h of e raised to power of j omega is equals to summation n is equals to 0 to m minus 1 Hn into e raised to power minus of h of j omega n. If we see or if we will discuss about its magnitude and its phase part, it can be, this function will be written as a mode of h into e raised to power of j omega and e raised to power j of phi of omega. So here this phi of omega will relate the or give the information regarding the phase of the filter, while this mod part will give the information regarding the magnitude part. The magnitude and phase response is given by mod m of omega is equals to h of e raised to power of j omega, which is equals to real part of h into e raised to power j omega square plus imaginary part of h into e raised to power of j omega square whole power is 0.5 or 1 by 2. So we can calculate it, while also this will the magnitude and the phase is given by phase will we can calculate with the help of phi of omega, that is the tan inverse of imaginary of h into e raised to power j omega, and it is divided by real part of h of e raised to power of j omega. So, when we will explore this part, the first one equation for the discrete time Fourier transform. So, it can be subdivided into the two categories. That the first one, that is the magnitude part and the phase part. These two are given by the equation number 1 and the, let us say, equation number 2. So, the filter can have a linear or non-linear phase characteristic which we have to focus. So, the either they will be linear or non-linear depending upon the delay function. So, there are the two types of delay here we have to consider, that is the namely that are the phase delay and the group delay. So, we have to now with the help of these two equations, now we have to calculate the its time phase delay and the group delay. So, the phase delay and the group delay are of the filters are given by the tau is equals to, first one, tau p, this is equals to minus of phi of omega divided by omega, and the tau g is equals to minus of d of phi omega over d omega respectively. For this phase delay and the group delay. So, the linear phase. So, with the help of these two parameters, we have to calculate for the equation 1 and 2. That means, for the specifically to the equation number 2, that is the phase delay. Phase. So, phase have constitute two parts, phase and group delay, which is defined by the this function. So, the linear phase filters. So, we can with the help of these two, we can say that the linear phase filters are those filters which have phase delay and the group delay, that is tau g, is constant. Constant means what? The independent of frequency. Independent of frequency. So, the linear force. So, with the help of these two parameters, if we will evaluate these two things, that is the tau p as well as the tau g calculate, we will calculate these two values, and if these two values will be constant, then we can say that the system which we are going to design for FIR filter, they have satisfied the linear phase characteristic and the FIR realization can be possible. So, now what will be the value of these two? What the final values we have to calculate, the condition, we have find out that if these two things will be constant, so what is its consequences? What the consequences has to be come? So, now we will go for the derivative part for this phase part. This one we have to now focus what is the its analysis we will do and find some concluding remarks. On the basis of that, we can say that the filter should be linear. So, for the phase response to be linear, now this will our main interesting part that we have to take it into the consideration. So, the phase response to be linear. So, the phase response is equals to phi of omega by omega, which is equals to minus tau, that is our phase delay, where this omega, the omega is ranging from minus pi to pi, greater than equals to less than equals greater than equals to minus pi, but less than equals to pi. So that what will become phi of omega is equals to minus of omega tau here. Now we will calculate its value, where this tau is a constant phase delay. This tau is a phase constant delay expressed number of samples. Now we will evaluate it. So from the previous equation that we have written here, the 5 omega is equals to tan inverse of imaginary part of h into e raised to power j omega. So we can write it like phi of omega is equals to tan inverse of imaginary of h into e raised to power j omega, or real of h into e raised to power of j omega, and this value equals to minus of omega tau. So now we can write this equation, that is phi of omega is equals to tan inverse imaginary part divided by real part is equals to minus of omega tau. So we can write it like omega tau is equals to tan inverse summation of n is equals to 0 to m minus 1 hn sin omega n divided by summation of n is equals to 0 to m minus 1 hn cos of omega n. So the above equation can be now converted. So how can we are able to write it like this? Imaginary part equals to hn e raised to power of j omega sin omega n hn, as we have discussed here in the first one, that is hn, this part hn is equals to e raised to power minus of j omega n. So the iota term can be changed, e raised to power minus j theta, we know that cos theta plus minus j sin theta. So as per this function, if we see here as this part, if we can see, so this part can be written as cos theta plus minus of j sin theta. So when we will compare it, this one to break it into the real part, so this is our real part and this part is our imaginary part here. So on the basis of that, we have to write the real part will become cos omega n and the imaginary part will become from this equation minus of sin omega n. So minus will be cancelled out from minus omega tau. So we can able to write here this one hn sin omega n upon hn of cos omega n here. Now we will consider it, continue. So we can change it sign. Tan of omega tau is equals to summation of n is equals to 0 to m minus 1 hn sin omega n cos of omega n, or this tan omega tau we can also write it like this, sin of omega tau upon cos of omega tau. So we can write it. So the equation now will become this one, hn sin omega n divided by n is equals to 0 to m minus 1 hn. So this is the now another equation will create here. So now we can make it cross multiplication. We can now make it its cross multiplication here for these two for the solution point of view. So we can now write it like this, summation of n is equals to summation of n is equals to 0 to m minus 1 hn cos omega n cos of omega n into sine of omega tau, cos omega n into sine omega tau is equals to n is equals to 0 to m minus 1 sine omega n into cos of omega tau. Now we can solve it further. Summation of n is equals to 0 to m minus 1 here. Summation of n is equals to 0 to m, hn will be taken common out. So we can write it like sine omega tau into cos of omega n minus of sine of omega n into cos of omega tau, which is equals to 0. So this can be now looks like this one. So when now also therefore, so in the generalized way, the equation in the generalized sequence, when we will further solve it, so therefore we can also write this equation equals to the other equation equals to n is equals to 0 to m minus 1 hn sine of omega tau minus of omega n is equals to 0. So we have calculated or derived this equation. Let us say the equation number is 3. We will a notation for this equation, that is the 3, that is summation n is equals to 0 to m minus 1 h of n sin omega tau minus omega n is equals to 0. That we will get this result with the while we have analyzing the phase response, that is phi of omega part. So when the solution of the equation number 3, when we will solve for the, when we will expand this one part, n is equals to 0 to m minus, let us say sin omega sin h0 sin what it will become omega, then sin omega will be sin omega tau, then n we will put the value sin n minus h1, फिर h2, then h3, like it will, we can expand it till the m minus 1 minus of n time. When we will expand that, and we will check the similarity, when we will check, so the solution we will get for this equation number 3. The solution of this equation will say that the value of this tau, the phase delay, that is equals to m minus 1 tau, sorry, m minus 1 by 2 tau is equals to the solution part m minus 1 upon 2, the first one result, which we will get this one, and the second result we will get for the impulse response, that is h of n is equals to h of m minus 1 minus of n. So these two equation 4 and we will get the equation number of 5 for the condition is n is greater than 0 but less than m minus of 1. So the equation number 3, what we will get from the phase response characteristics, when we will evaluate the phase response of an DFT of an impulse response h of n. So the equation number 3 we will get, and when we will solve it, expand this equation from the n is equals to value of n, samples value, sequence value from n is equals to 0 to m minus 1. The two concluded remarks we will get in the solution, that the first one, the tau phase delay is equals to m minus 1 upon 2, and the h of n is equals to h of m minus 1 minus n. So the two things we will get here, the first one, that is the tau p, that is the tau p and tau g, that are the phase delay and group delay, should be constant. The first one, also along with this, the two result we will get, if we will check the linear phase characteristic, the tau value is equals to m minus 1 by 2, and h of n, impulse response, should be equals to h of m minus 1 minus of n. So here, with the help of this, we will get the X symmetrical condition. Is these two statements, the phase constant and group constant, phase delay and group delay should be constant, and these two equation 4 and 5 will be satisfied. Then we can say that the linear filter for any system we will design, it should be an FIR. So these two characteristics, these characteristics we will verify while designing any FIR filter for any given system or any transfer function. So thank you from my side. This is the overview for some generalized characteristics for the linear phase characteristics for the designing of any FIR filter. The reference I have taken, that is from the book Salivanan. Thank you and Jai Hind.